All right, so how are you guys doing today?
Good. How are you?
Good. I'm good, thank you. So this is the third review, right? So to be honest, there's nothing much left to cover. So I'll try to cover the ones I wanna review today, and then I'll let you stay if you want, so you can ask me any other your own questions. Like I said before, on Friday, you might have some of your own question about the exam or anything, any subject. You can ask me after the lecture. All right. So the few things I want to go over today. The first one. Okay, so I'll give you about 1 minute, and then think about which one will be more stable. So by the way, what is this called? Back and forth? Ring flip. You guys remember the ring flip term? So when you have a chair conformation of the cyclohexane, but you have one methyl group there. So it's methyl cyclohexane, but they do ring flip, okay, over here. So which form is more stable? Can you guys guess? Maybe 1 minute. To best way to approach this question, draw the hydrogen implied in the structure. Okay, about 1 minute. We'll do this together anyway, but it is important for you to try this one first in your own way. So when we do it together, it makes more sense. Okay, so let's do this together. So which one do you think is more stable, A or B?
I think B.
So okay. So here's the thing. So whenever you have this is what we call axial position. Okay. It's like a y-axis. Okay. And this is we call equatorial. Equatorial. So like somewhere on the plane, like the position. Okay. So if you have a one that is axial position over here, what they're going to experience is this is 1,3 diaxial interactions. Because this is Turkey with the hydrogen. So those hydrogen imply on those positions, axial position, or interact with each other, okay, here. So they're going to have a 1,3 diaxial interaction. So 1,3 diaxial interaction is because of this bulky or some hydrogen nearby, those two hydrogen too. So it's all kind of a steric string. Okay, but here in this methyl group on the equatorial position, that only has the one Gauss conformation. This is the methyl group. Oh, not Gauss. I'm sorry. This is it's not experiencing any 1,3 diaxial interaction over there. So whenever you have one methyl group on your base in A and B, this is more preferred form conformation between these two. Okay? Because they don't want to experience the 1,3 diaxial interactions. If you put that methyl group on here in equatorial position, they don't have to experience the 1,3 diaxial interactions. Okay? So if you compare the stability of A and B from this ring flip conformational change, they will prefer to in this one. Okay? So A will be more stable. And it means this A form is more preferred in this example. Okay? Makes sense, right? Do you guys remember this actually? It's a bit on the YouTube channel. Okay. So anyway, so let's move on. That makes sense, right? Okay, then how about we have two method groups. Two. So I'm gonna put this one over here, okay? One, there are two now, not one. Okay. Okay. And then you're gonna put this one here to here. Okay. Okay. And then this is A and B again. And once again, try to find the most stable form. It will be A or B. Same here. You can try to draw the hydrogen and see if they do any 1,3 diaxial interaction or anything like that. Try to draw the hydrogen, implied hydrogen, and see if there's any interaction they go through, or maybe other conformation. Okay, so what do you guys think? Which one is more preferred? The answer is neither. They're equally same stability here. Okay, so if you have a two methyl group here, so these two ring flip over here, right here and here, they all have a axial position methyl group over here and equatorial position over here, right? Okay. So if you look at this one here, this is equatorial up, this is axial up. So these two methyl groups are heading almost the same direction based on this plane, on this cyclohexane here, base. So this is what? Is a cis or a trans? Can you guys guess? Cis, perfect. So this is the cis 1,2 dimethyl cyclohexane. So in this case, you don't have any preferred form because they will show you the same stability. This one obviously will show you what? Once again, 1,3 diaxial interaction here and here. There's one more thing you need to know is because of this, the sixth, so here to here, if you look at this one over here, It's also a Gauss conformation strain over there. So it has one free diaxial interaction and one Gauss interaction over here. But this is the same here. This one will experience the 1, 3, the diaxial interaction here, and also this one and this one also show you Gauss conformation strain too. So they all experience the same discomfort. So meaning technically it will not be preferred to any form of these two, but equally same. So it'll be just there will be no more stable or less stable form between A and B if it's a cis. Okay, makes sense, right? You guys remember this too? I also did it on the YouTube channel if you want it again. But once again, there was one good question at the beginning of this class. You don't have to memorize the number though. It's okay. But this is just you just need to know which one is more stable or preferred based on this theory. So then let's do one more. Okay. So if this is a cis, okay. Is my drawing okay today? Okay. So if that is the case, let's try to trends. Okay. Trends. And I'll give you also 1 minute. Okay. This is also dimethyl, but trans dimethyl cyclase. You see it's up and down, up and down. Okay. Oh, A and B. Okay. So which one is the more preferred? So try to draw the hydrogen again, especially the one on the axial position. So that is a trans 1,2 dimethyl cyclohexane. Okay. In this case, this is different from the cis one. Okay. So let's talk about it. Try to draw the hydrogen on the cyclohexane base. And see what happens to them. Okay. Then you have a 2 methyl group on trans position. Try to see where they are and see if there's any interactions they may do on the compound. Okay, so what do you think? Which one is more stable? A, perfect. Great. So here's the thing. If you look at there's 2 axial methyl groups on this base. You have this is up hydrogen axial position doing 1,3 diaxial interaction on here. There is a down hydrogen also doing 1,3 diaxial interaction on this side as well. So these two will create great amount of the strain, great amount of discomfort, great amount of the energy to overcome to keep this form. So this is very unstable. Because they don't want to be in this position to experience the 2 separate, like a 1,3 axial interaction, which is too much for them. So they will not be in this form unless they have enough energy to do so. So it's not very preferred. But this one is better because the only thing you have to think about is these 2 methyl groups on here are all in equatorial position. So those are in the equatorial position. They don't have to experience those 2 types of strain, but just one Gauss interested because they're just 6 degrees away from the front and back. So that's the only thing they experience, which is a lot better than these two grid minus string. So this is more preferred, which is relatively speaking, A is more stable than B. Okay? So this will be preferred between these two. Okay, makes sense, right? So the point is whenever you compare the sterility of the compounds, you can also in the Taylor conformation try to draw the hydrogens implied, especially on the exit position on the compound. Then it will tell you how much of strain or discomfort the compound should go through. So more discomfort they go through will become more unstable. If it's less, it's more stable. Okay? Makes sense, right? Okay. So let me try to. Okay. There's actually not much that you can do today. You can try this one, okay? One more time. Yeah, okay. So let's try to do Kyrori Center RS configuration on here, okay? I'll give you about 2 or 3 minutes. It takes some time, I know. So try to do the RS configuration on this Kyrori Center. About 1 or 2 minutes. We did almost everything already. Okay, about 1 minute. Okay, so let's do this together. So this group will be number, this one will be number, if we prioritize those 4 groups, there will be number, what number it will be this one? So whenever you prioritize this one, this will be 1, 2, 3, okay? It's because this is all same carbon here, I know. But this will have a O from this neighboring elements over here. This will be carbon, carbon, carbon. So C, C, C. This is a hydrogen, hydrogen, hydrogen. It's a CH3. So this is the same as this, right? Okay. Hydrogen, hydrogen, hydrogen. So obviously, atomic number wise, this is higher than this one. This is higher than this one, so it'll be 1, 2, 3. Okay? So in this case, this will be 1, 2, 3. So it'll be S. Perfect. And also, luckily, we have number 4 heading back. So we don't have to do anything about that. Okay, just wait it is the answer. Okay, so if I change this one to in this way, okay, in this way, it could have been what? R. Perfect. Good. But now it was for sure S when we had it before. Okay, makes sense, right? Good. So I'll just do one more, and that'll be all for today. Okay, these two. What is the relationship between these two? You can say they are same compound. You can say they are diastereomers. You can say they're enantiomers or enantiomers, either way you can say it. But it's mirror image to each other, or yeah, you can just go ahead. It's not constitutional isomer for sure because it has all same bonding there. But among the lots of stereoisomers, which one will be? Or it will be the same. Okay? That's the question. So to know that, you need to do RS configuration quite a time. Okay, this takes quite a time, so I'll give about 2 or 3 minutes. So you have to do RS configuration quite a time. Okay. Remember, there's always, not always, but there might be a implied hydrogen. Okay. Try to think about that one. That's the first step. Okay. First step. So one more minute, we'll do this together. So try to find out how many chiral center first. And then we can try to do that. Okay, 30 seconds. This will be the last one we're gonna try. Okay, so how many chiral center here? Can you guys guess? 2, right? It's this one. Makes sense, right? Because this is the carbon that has 4 different groups. Here, 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 here. Okay. So obviously we have a 2 chiral center here. Because those are the same. Now there's chlorine, so no. So anyway, so if you look at this one over here, it is O. So this is obviously prior to the carbons here and here. So this is obviously number 1. And this one and this one carbon has carbon, carbon, hydrogen, right? Carbon, 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 hydrogen. Okay, it's carbon, 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 hydrogen. This one has a chlorine, carbon, hydrogen. Okay, so which one is higher? You look at the periodic table, which one is higher? Chlorine, right? Because carbon, carbon, hydrogen, perfect. So there'll be 2 and 3. Okay? And luckily, once again, you have a hydrogen heading back, so you don't have to change anything. Just 1, 2, 3. So it'll be this way. So it'll be that's perfect. This is S. Makes sense, right?
So there's 2 points or 3 points?
What do you mean?
Chirality points.
2.
Okay.
We're doing this one first. Yeah. So let's do this one, okay? Makes sense, right? This is S, right? Okay. So this one is, so we have a 2 chiral center. So then this one has the 1, 2, 3. Can you guys see that? This is a chlorine, but these 2 carbons, but this is what? Bound to O, carbon, hydrogen. This is the hydrogen, hydrogen, hydrogen. So this is prior to this one. So it'll be 1, 2, 3 on here. Okay? Do you see, right? Do you guys see? 1, 2, 3. So, and also your number 4 is heading back also too. So you're lucky. 2, 3. So this is what? This point is R. Are we good? Makes sense. Okay. So the, but here your position is embodied there. So this will be, you can do it. I mean, but I know it's R, because it's heading front. So you have to look at it on this side. But they're all the same. So it'll be just R. Okay. And we didn't change anything over here. It's all the same. So this will be R. Okay. So you have S, R, chiral center, and R over here. Okay. So the relationship between these 2 is diastereomers. So diastereomers means whenever you have more than 1 chiral center, if there's some chiral center shows different RS configurations, you can say it's diastereomers. If it was in this way, okay. If it was in this way, it could have been here, right? So if you change this one, now you have a number 4 is heading front. So you also need to look at this on the other side as well. So it becomes S. If you change this one over here, and then what? It's SR, RS. And what's the relation between these 2? Will be enantiomers. Perfect. That's the difference. So when you check the chiral center and put R or S, whatever that is there, and then if they are all like embodied in all position, that means that they are mirror image to each other. But if there's one point at least different, you can say diastereomers. Okay. But the other is the same, but just 1 or 2 or 3 are different, you can say diastereomers. But they're all embodied on each position, mirror image. If it's not, diastereomers. Make sense, right? Alrighty. Oh I'll just stop here today. That's it.